Hello everyone, in this video we are going to discuss about interrupts and interrupt handling in operating system. These are the topics we are going to discuss. So imagine you're sitting at home waiting for an incredibly important package to arrive. You have two choices. Option 1, every single 60 seconds you walk down the stairs, open your front door, check if the delivery truck is there and walk back up. You do this all day. You can't watch a movie, you can't read, you can't cook. Sounds absolutely insane, right? In computer science, this is called polling. And if early computer engineers hadn't solved this, your modern operating system would be completely unusable. If your CPU had to manually check your mouse, your keyboard, your Wi-Fi card, and your internal drive every few nanoseconds to see if they had data, it wouldn't be have any time left to actually run your games, render your videos, or compile your code. So how do operating systems escape this loop? They use something brilliant called interrupts. In this video, we are unpacking the asynchronous symphony that happens inside your computer every single microsecond. Let's dive in, guys. At its absolute core, an interrupt is a hardware or software generated signal that tells the CPU, stop what you are doing immediately. We have an emergency event that needs your attention. Think of it like a doorbell. Instead of you checking the door constantly, you sit back, work on your laptop, and let the doorbell alert you when something happens. When a peripheral device, say your keyboard, wants to send data, it asserts a signal on a specialized physical wire called the interrupt request line or IRQ. This line feeds directly into a piece of silicon known as the programmable interrupt controller, which acts like a triage nurse in an emergency room, prioritizing which device gets to talk to the CPU first. The moment the CPU receives the signal, it finishes executes its current atomic instruction, hits the pause button on your active application, and shift gears entirely. But how does it do this without losing your place or crashing your computer? Before we look at the recovery process, we need to understand that not all interrupts are created equal. They fall into distinct categories. First, we have asynchronous hardware interrupts. These are completely unpredictable. They come from the outside world. When you click your mouse or a file finishes downloading onto your SSD, that hardware component signals the CPU. It doesn't care what code the CPU is currently executing. It's an external trigger. Second, we have synchronous software interrupts. These are entirely predictable because they are generated by the software itself running inside the CPU. When a user application needs to perform a protected action, like creating a new file on the disk or allocation memory, it cannot do it directly due to security ring boundaries. Instead, it executes a special construction to deliberately trigger a software interrupt, handling control over the OS kernel safely. And finally, we have exceptions or traps. These are accidental software interrupts. If a program attempts to divide a number by 0 or tries to access an address in RAM that doesn't belong to it, a page fault, the CPU interrupts itself to let the OS handle the error gracefully instead of letting the entire machine blue screen. So the interrupt signal just hit the CPU. What happens step by step behind the scenes? This is where the operating system shows its true engineering elegance. The absolute first step is state preservation. The CPU cannot just away blindly, it has to save its current train of thought. It takes the program counter, which points to the exact next line of code to execute, along with current CPU registers, and pushes them safely onto securely memory structure called the kernel stack. Once the current state is frozen in amber, the CPU looks at the numeric ID of the interrupt. It uses the number as an index to look up a lightly critical array in memory called the interrupt descriptor table or IDT. The IDT is basically a master phone directory. The CPU checks the index, finds the exact memory address of the function designed to handle that specific event, and jumps straight to it. This function is called ISR or Interrupt Service Routine. The ISR runs rapidly, clears the hardware device's buffer, does the vital work, and then executes a specific assembly instruction. Interrupt return. The CPU pops the saved state of a stack, reloads its registers, and the program resumes so fast that you, the user, never felt a single nanosecond of hesitation. This elegant dance happens millions of times a day on your machine. When playing a fast paced competition online game, your network card is receiving fragments of game data continuously over Ethernet or Wi Fi. Every batch of packets triggers an interrupt to ensure the data is moved out of network card's tiny internal buffer and on into system RAM instantly, preserving those critical low ping frame updates. But what happens when this system is pushes to its absolute limits? What happens if a network card malfunction causes it to fire interrupts endlessly, millions of times a second? This triggers a catastrophic scenario is known as an interrupt storm. The CPU spends 100% of its clock cycles simply preserving states, looking up the IDT and executing handlers, leaving zero time to actually run the OS scheduling loop. This system completely freezes, a state called an architectural live lock. To prevent this, the modern OS kernel split interrupt handling into two phases, the top half and the bottom half. The top half is ultra fast. It saves the data, tells the hardware got it, and it terminates instantly. It defers the heavy processing of the data to a background worker queue. The bottom half allowing the system to balance urgent hardware notifications with regular app workflows smoothly. As we push deeper into the future of computing, hardware is getting faster at an exponential rate. Today's enterprise cloud data centers run on a network backbones pushing 200 to 400 gigabytes per second. At that extreme scale, even the ultra optimized top half bottom half interrupt model starts to fall apart. The pure CPU overhead of context switching, saving registers, and entering kernel space hundreds of thousands of times per second consumes massive amounts of power and processing overhead. Because of this, the cutting edge of operating system design is actually moving away from traditional interrupts for ultra high performance pathways. Technologies like DPDK, the Data Plane Development Kit, allow user space applications to safely bypass the operating system kernel entirely and pull high speed hardware queues directly using dedicated isolated cores. Furthermore, modern AI accelerators are building autonomous event routing logic right into the physical design of the chip architecture, reducing reliance on traditional CPU interrupts. This brings us right back to our opening puzzle. We started by looking at the deep inefficiency of a CPU trapped in an endless loop of checking its own door for a work. The interrupt mechanism was the ultimate historical breakthrough that unlocked true multitasking, transforming our computers from rigid calculations loops into the fluid, beautifully responsive machines we rely on today. From that single mechanical keystroke walking up the processor to the massive distributed cloud infrastructures routing global traffic, interrupts act as the unsung conductor orchestrating the digital symphony inside our silicon. So if you enjoyed this deep dive into the inner workings of modern operating system, Make sure to hit the like button, subscribe to our channel, and drop your questions or thoughts in the comment below. Thanks for watching, and I will see you in the next one.